Bắt đầu.
Record nha.
Cứ record đi xong rồi cắt ra cũng được.
Okay. Hey everyone, I'm Dương Phước Lộc, and today I'm here to present the topic electrical fault detection and classification. Here's the content of this topic. So we move to introduction. Fault detection is critical for maintaining the stability of power transmission system. This is because undetected fault can lead to serious consequences in class power outage on a large scale, disrupting both household and industrial. Server equipment damage, which can be costly to prepare a reflect significant financial loss, adding further burden to anti-liatier and stakeholder, therefore ensuring time and accurate fault detection is not just important but essential for modern power system. And to address their challenges, fault detection system must be both accurate and efficient. So why? This is because their quality are vital to minimizing system downtime, ensuring a consistent power supply, maintaining high reliability in grid operation, especially in the face of growing demand. To better understand the scope of the problem, let's examine some common fault type. Like you can see here, LL fault, line to line, that means a fault between two phases that can disrupt balance in the system. And here we have LLL fault, that is three-phase fault. That's a fault involving all three phase, typically small servo. And we have three-phase fault to group fault. A fault involving all three phase and the group, often causing a big damage. So let's talk about the traditional method of fault detection and the challenges associated with them. Traditional methods have been the backbone of fault detection for years. Here we have three traditional methods. As you can see here is Fourier transform and wireless transform. We have distance protection relay, and we have phasor measurement units. Fourier transform and Weisley transform are the methods analyze signal frequency and time domain to identify anomalies. We have distance protection relay rely on fixed threshold to detect fault based on independent measurement, and we have phasor measures units. This method provides synchronized measurement of electrical waves, which have monitor power grids. So the chain of traditional methods are here. We have for Fourier transform and Weiss transform, just effect for linear signal. They struggle with nonlinear signal and dynamic boundaries, which are common in model transform life. And distance protection relay is not adaptable static threshold. And finally, we have phasor measurement units is just limit for dynamic risk. So the problem here is that they are all lack of adaptability. Traditional methods operate on fixed threshold, making them suitable for dynamic and complex power systems. They are primarily designed for simple linear signal, and they are slow and inefficient too. Therefore, detection and response time are often long, leading to delay in system recovery and potential casting fault. So that's why we propose a solution that utilize machine learning for fault detection and classification. So firstly, we talk about why is machine learning. As highlighted in the first section, traditional methods for fault detection often fall short in modern complex power systems. Their method, while effective in simpler setup, struggle with adaptability to dynamic grid condition and non-linear behaviors. Machine learning, however, address their limitation by leveraging its ability to adapt to evolving scenarios and handle large datasets. This adaptability does make its particularity well suited for modern grid. So the advantage of machine learning is that they very adaptability, and because it's learned from both historical and real-time data, ensuring it stay relevant in rapidly changing environment, and they and the prediction is accurate for detection and classification. The efficiency is reduced detection by time, and robustness is reliable in complex environment. Is the impact of machine learning on risk system and for discuss knowledge accuracy, improve risk reliability and stability. And so for managing model risk complexity. So we come to material and methods. First, I talk about case study. We had model a power system in MATLAB to simulate fault analysis. The system consists of 4 generations of 11,000 trees, each pair located at each end of the transmission line, with transformer in between to simulate and study the various faults at the midpoint of the transmission line. The dataset we have here is that we simulate the circuits under model conditional as well as under various fault conditions. We then collect and save the measurement, the measure like voltage and like current, and at the output side of the power system, we simulate nearly 12,000 data points, and then the data is labeled.
About the workflows, we put class data and detect data into AI Studio to separating the feature. Next, we put it into model and evaluate the effectiveness of the algorithm. About the data visualizations and analysis, we split data into several status to visualize voltage and current graph and summarize the features of false and non-false status. As you can see, there was about 6,505 non-false status and 5,496 false status. Next, chuyển slide chưa? Đến slide 10. About the detect no false status, the graph has the vertical axis as the voltage and current parameters, and the horizontal axis as the E element of the file. We can compare it with file status to choose the main feature. Next is slide 11. The detect file status. As you can see, the maximum voltage graph of both states range from 0.6. Meanwhile, the current graphs show the clearer difference when they are spread over the 100 to 700 range. We will take the current parameters as the main features for the algorithm. In slide 12, we have the new file is class data. About non-fault status, we have the graph of current and voltage, like sin functions that has the equations and a rule. It's like 30. We have the light ground file between phase A and ground. 14 is the light line ground files between phase A, phase B, and ground. In slide 15 is the line to line files between phase A, phase B, and phase C. And the last one is on files between the phase A, phase B, phase C, and ground.
Ê, tao vẫn đang thấy cái slide ở màn hình là random forest này.
Tao chỉnh là 17 mà. Thế á?
Nhảy rồi.
Thế tức là nãy giờ là mày thấy là ở random forest hả?
Nằm ở random forest hết.
Thế bây giờ khác chưa?
Tao cũng chả hiểu. Bây giờ mày chỉnh thế nào? Mày bấm chỉnh.
Dũng bị lại, nó nhảy rồi đấy. cứ tiếp đi.
Thôi tí xem record tính sau.
Đến bao nhiêu
Okay.
nhỉ?
About the material and method in slide 17. The first algorithm is linear regressions. The application is predict the continuous output based on linear relationship between input and outputs. Predict continuous false state using current and voltage. Other model evaluations, we use mean square errors and coefficient determination. Next algorithm is naive Bayes. The application is classifies files assuming the feature independence, effective for data with Gaussians, and the model evaluation is compare the accuracy. Here is graph about the voltage and current. At the top, we have the voltage graph, and in the bottom, we have the current graph. In probability distribution graph of two classes, range 1 and range 2. Range 1 is red and range 2 is blue. The vertical axis represent the densities, which indicate the likelihood of the over specific feature. Value the VA, the voltage of VAs occurring in each class. The higher values on the vertical axis, the greater probabilities that voltage of VAs belong to that class. When the two probabilities density curve intersect, the intersection point plays a crucial role in naive Bayes algorithms, that is represent the decision boundary between the classes. Slide 21 is about the decision trees algorithms. The application is classifies files using range structures based on the rule condition. Each node represents a treehouse, and each branch leads to a specific class. The advantage of this is easy to understand and visualize, and it has a high accuracy for electrical fault classification, not detection. And here is the trees. The parameter is numeric, so we will use comparisons to create the branch for the binary tree. Range 1 is no file and range 2 is file, similar to 0 and 1 status in detect datasets. The binary tree's branch start from comparing current of phase B and map 60,000. Landmark, no, minus 65.41 401 and 417 and 102.405. Next is point current of phase with milestone of 76.668 and minus 90.287. And next, the current of Cs with about 110 to 111. Then return to current of phase and phase E with the number in this slide. And the final step is current of A about 69 0.116. And you may have noticed that we did not consider the wanted component due to the removal comment in the visualize chapter. About the random forest. Random forest is the algorithm which has many decision trees connected. The application is applicable to both classification and regression tasks, and it is resistant to overfitting and perform well in noisy, unbalanced datasets due to assemble nature. Advantage is provide insight into the importance of feature, aiding in dimensionality reduction and model interpretation. It handles large datasets efficiencies and can process both numerical and categorical data without extensive preprocessing. Here, slide 24 present the two of trees of random forest. The random forest is synthesized from many decision trees algorithms. Thus, we can get more features for each decision tree branch. For example, in the first decision trees algorithms, we focus on current, but second algorithms add the information from the vantage. Within the limits of the problem, we use the 60 decision trees to work, ensuring that we get enough features from the stream data and apply them. Now it's a simulation result. As I say, we use the root mean square error to for linear regressions. Root mean square errors is the square root of mean square error. Root mean square errors provide a measure of how well a model predictions align with the actual value. It's similar to mean square error, but is often easier to interpret since it is in the same unit as the original data. And here is formula of root mean square error. In this case, we have the root mean square error about 0.493. For this particular problem, whether a root mean square error of 0.493 is considered good or not good depends on the problem of the scale data. If the predict values is in the range 0 to 1, then the root mean square is quite large. Here is about the results. You can see, in fact, the range of predict error and non-error values is not large enough for us to classify both 0 and 1 below to 0.5. In slide 27, we have the accuracies to compare three of algorithms. Accuracies formula is equal to number of correct predictions divided to total number of predictions. And we have the, as you can see, we have the Naive Bayes is lead the accuracy. Next is random forest, and the last one is decision tree. About runtime and scoring time. Runtime is the time it takes to train model on the datasets. The formula usually depends on factors such as the number of samples, the number of features, and the complexity of the model. In scoring is the time it takes for the model to predict the output for the new datasets. So scoring time is usually lower than training time, especially for the simple model. Here, the green one is total time, and we have the random forest list the total time. Purple point is scoring time, and we have random forest list scoring time too. So that is tree and Naive is more efficient. So in conclusion, in general, each algorithms has different suitabilities. However, with its datasets in the decision tree algorithm is the most suitable algorithm. No, it's not decision tree. It's naive Bayes because it leads the accuracy and have the runtime error small. The model is in article available functions, and in the future we can create our own function to expectation of graduate student. From there, we can develop the algorithms based on the original, but more suitable and effective. And the last one, I want any questions for you to my group.
Okay, I can see your group topic is detect the fault in the transmission lines using the machine learning, right?
Yes.
So can you explain the challenge to do the traditional method in a electrical fault phase and why the traditional method is less effective for compared to the machine learning model, and could you provide the explanation?
Okay. I think I will explain this question. Yeah, and you can see traditional methods like, for example, like Fourier transform, phasors, measurement units, and distance processor relay have been widely for fault detection on transmission line. Fourier transform, for instance, analyze um, signal in the frequency domain, making it effective or identifying periodic change or disturbance. However, Fourier transform structure with nonlinear signal and has poor time resolution, which is a significant drawback given the transient and nonlinear nature of fault on modern transmission line. So their limitations are the needs for advanced techniques like machine learning, which can adapt to real-time change, handle complex screen scenarios, and improve fault detection accuracy on transmission line. And that's my answer. So,
Can you back to the slide of the decision tree algorithm?
okay.
Why your accuracy of the decision trees, the decision tree algorithm is quite low? Why it?
Okay, to answer these questions, we move on to the slide 22 and slide 24. In slide 22, as you can see, I only take data from currents of phase A, phase B, and phase C as the comparison features. And in slide 24, in random forest, we can take all the current and voltage feature. There are questions that why I why can I put more features on decision trees? I cannot take too many features because if I do, the tree dash it limit is not set, and it will continue to branch until each leaf contains exactly one sample, or there are no more features to split. Also known as oversplitting. Then this leads to the model remembering each training data samples instead of learning the general rule, also known as overfitting. And that's my answer. Any questions of other people?
Okay, I have a question for you. And why the linear regression algorithm should not use accuracy to check, but should use RMSE?
To answer these questions, we move on to the slide 26. You help me look. Slide 26.
Okay.
The simulation results of linear regressions. So the accuracy typically measures the rate of correct predictions in classification problems, where the prediction and the actual label discrete value, such as 0 or 1 or 2 or 4. In regressions, the model outputs continuous and comparing predict value to the actual values to see if the accuracy is meaningless. For example, the predict values is 1.427, although very close to 0, but it's not considered a correct prediction. That's my answers.
Okay, and I think we can end now.
Okay. Thank you for the listen.